Alright, so yesterday we were talking about sampling distributions and how they come about. What's really nice about the first page of notes here today is it's really a summary of some of the things that we were talking about yesterday. So there's really three terms that we want you to understand from, or to really start this section. And those are, what's a population distribution, a distribution of sample data, and then our sampling distribution. So this diagram really lays it out nicely. What you do is, or what we have is our population distribution. Okay? So for instance, the example that we used yesterday in one of our example problems talked about a bag of poker chips where you had 100 blue chips in the bag and 100 red poker chips in the bag all mixed together. So you can see here, this graph actually displays your population distribution. 100 blue chips and 100 red chips. Then it has here basically a parameter calculated out for you where P is equal to 0.5. You can think of our parameter as the proportion. P is equal to the proportion of red chips. So then, what we do is we start to take samples. So we start to take simple random samples of size 20. That's what we were doing a little bit yesterday. So what happens here is each of these displays right here are an individual sample of size 20 and are three different potential results you could get. You could get all sorts of different results. So like here on the first one, we got 8 red and 12 blue. So the sample proportion P hat was equal to 0.40. So then on the second one here, it looks like it's at what, 11 out of 20, so the sample proportion, 0.55. Then on another one here, we got 13 out of 20, so 0.65. Each one of these represents a distribution of sample data. It's one outcome. Okay? So it's like collecting or just doing one sample. What we like to do and take a look at is what's called the sampling distribution. It takes a look at all samples of size 20. And we start to take a look at what that distribution looks like. Now it's really difficult to do all samples, but as we start to do many samples, the distribution, or we start to get a picture of what our sampling distribution would start to take a look like. So down here, we just simply define everything. So again, our population distribution was the individuals are the 200 chips. The variable was their color. The distribution of sample data is just simply showing the values or the variable color for the individuals in each sample. So we're calculating out the sample proportion of red poker chips. And then the sampling distribution is the collection of all of these sample data collected, and we get our distribution. All right, so to kind of take you through another one of these where we're going to kind of set it up and take a look at this, and before we actually do, here's one thing that I want you to know. Here was our parameter. What do you notice about our distribution here, our sampling distribution in the center? Okay, it's 0.5, which was our population parameter. They're basically the same value, and it's centering around that. So let's take a look at this example down here. Mars Incorporated says that the mix of colors of its M&M's milk chocolate candies is 24% blue, 20% orange, 16% green, 14% yellow, 13% red, and 13% brown. You can actually find this on their website. They actually have color distributions for all their different types of M&Ms that they make. Now given, they have different color distributions also for the seasons too. But why is it this particular distribution? I don't know for sure, but my guess is it has to do with cost and also has to do with how the candies look. Does this color distribution all together, does it make it look more appetizing? So if it makes it look more appetizing, people are going to eat more of it. Okay. So now, we want to examine the proportion of orange M&Ms in repeated examples of 50 candies. So here it says, graph the population distribution. All right, so this is going to be our population distribution. So in our population distribution, right, here we're told the percent, so it goes all the way up to 24 as our highest, so I'm going to count by fives. 5, 10, 15, 20, 25. And I'm going to graph each and every one of the colors. We'll see if I can actually color code it to an extent. So we start off with blue, 24%. Orange is at 20%. Green, 16%. Yellow, we'll see how well yellow shows up. It's showing up okay?
What's the percent?
Yellow is 14. It actually shows up okay. Red is 13. And so is brown. I actually had all those colors. Nice. So we're asked to identify the individuals . So what makes up our individuals here? What are we selecting?
Colors.
Well, okay, so that's going to colors from what?
M&M from M&M's.
From the M&M milk chocolate candies. So those are our individuals. The M&M milk chocolate candies. From the candies, our variable is the color. So we noted all the different colors. So now the parameter that we want to measure, okay, proportion of orange. So the proportion So since this is a parameter, we would say P equals 0.2. Alright, so now B says imagine taking a simple random sample of 50 M&Ms. Okay? Make a graph showing a possible distribution of sample data. So we need to kind of imagine how many of each color do we have? So let's just kind of note them. I'm just going to use a different color here. So we have blue. Oh, that was supposed to switch to pink, but orange, green, yellow, red, and brown. So these all have to total to 50 candies. So if I were to imagine how many blue candies might be in my bag, how many blue would you might expect to be in there, roughly? Okay. Well, if it's 20, what's 20 out of 50? Okay. What percentage would we expect? According to the population, we should have what percentage? 24%. So, what's 24% of 50? Okay. So we would expect 12, but could we have some variability?
Yeah.
Sure. So give me a number around 12.
13.
13, all right. So now, let's do the same thing for orange. If we expect 20% of them to be orange, 20% of 50 is 10. Give me a number that's around 10.
9.
9, okay? Let's do the same thing for green. Green was what? Forget the percentage.
8.
Okay? 16%, so that's 8%, so you're going to say exactly 8?
8.
All right. How about for yellow?
7.
Okay, how about for red?
6.
How about for brown? What does it have to be?
6.
What do these have to add up to?
50.
They have to add up to 50. So 13, 9, 8, 7, 6. That actually adds up to, I believe, 43.
7.
So that has to be 7. Now, is this the only answer we could have? No. This could be 15, and this could be 7, this could be 10, and this could be 5. So, again, we're just doing one sample.
So for like, is it like doing it was 12 and then you did 13? How many numbers should you just stay with it if you're doing something?
Well, I would just say something within reason. So I wouldn't put like 40 because that doesn't seem to make sense. If you got a bag where you got 40 blue M&Ms, something was probably wrong with the way they sorted the or the way they mixed the candies in some way, shape, or form. Or maybe you got the bag that's, the $10,000 winner or whatever, because once in a while they'll have contests where it says like, if you get all of one particular color, I think like during Halloween, like if you get them all black or all orange, you like win the big prize or something like that. So the there's going to be some variability. You just want to try to, make a good judgment on what would be reasonable. Okay? So, now I have my results, so it says, make a graph showing our possible distribution. Okay? So this is going to be our sample data, okay? So this is our sample data. So here, instead of percent, we have frequency. Our biggest number was 13, so maybe I'll count by 2s, 2, 4, 6, 8, 10, 12, 14. And so let's go ahead and graph all those. I'll try to be color coordinated here. Let's start with blue. Blue was 13. Orange was 9. Green is 8. Yellow was 7. Red was 6. And brown was 7. Come here. Sorry. Now it says, give the value of the appropriate statistic for this sample. So our parameter was proportion of orange candies. So in our case, we had 9 orange candies out of 50. Okay. So if we go 9 divided by 50, that gives us 0.18. So our sample proportion of orange candies is 0.18. Notice how it says appropriate statistic. Now we're using p hat here. So it's very important that the notation stays consistent. Up top it was the population distribution, so hence why it's a parameter in p. Here we were doing one sample, okay? And we get p hat to be 0.18. Now, if I asked you to do this individually, my guess is that we could potentially have over 20 different answers or 20 different distributions. All right, so now let's take a look at the next page. Okay. Question C says, which of the graphs that follow could be the approximate sampling distribution of our statistic? Okay. Our statistic again being p hat, which is the proportion of orange candies. So if I look at this, is the first one, could the first one be the approximate sampling distribution? What does the first one look like? Okay, it looks like a bar graph of something like this, doesn't it, here at the bottom? Okay? So, is A, or this graph, is just one sample. Okay? So it's similar to a result. So this is similar to our graph in part B. So this one is not the choice we're looking at. So the question now becomes, does the second graph or the third graph seem to be the better representation of for our sampling distribution? So right now both the second and third graphs are graphs of sampling distributions, or I should really approximate sampling distributions, but but which one is the one that represents the one for orange candies? What's probably the best thing to look for? What did we notice when we did the red chips? What did we notice about our population parameter and our sampling distribution statistic?
They were the same.
They were the same. So, we expect, or the population parameter here is 0.2. So when I look at my sampling distribution, it should center around 0.2. This one centers around 0.2. This one, the center of p hat is at about 0.40. Okay? So we want to note that here. The second graph is the better choice, since the center of the distribution is at p hat equals 0.20, which is the same as our population proportion. So one of the characteristics of a sampling distribution is that if we take an infinite amount of samples, the mean or the center of the distribution will actually equal the population parameter that we're looking at. So in our case of orange candies here, it's going to center or hit or be at 0.20.
So do you mean population parameter?
Well, proportion in this case, since this was a proportion. Okay, so because if I go back here, the parameter was defined as the proportion of orange candies. So two of the things that will happen with sampling distributions that we want to understand from chapter 7. The first is this whole concept of the center. So when we talk about sampling distributions and we start doing it, we start to look at the center. We hope that the center is what we call an unbiased estimator. It is unbiased when the mean of our sampling distribution, or the center, is equal, and I'm going to say or very close to, the true value of the parameter that's trying to that you're trying to estimate. When those two are equal or really close, like for instance, if I did this sampling distribution and I actually calculated out the mean of all these values and it ended up being like 0.1997, I would definitely say that is a unbiased estimator. Okay? If it was like 0.201, I definitely would say it's an unbiased estimator. But if I got something like 0.23, I would not say it's an unbiased estimator. I would say it's actually biased when they're not equal to. Okay? Now the reason why I allow that a little variability is, again, because the sampling distribution is really hard to get all the samples. So we're always going to base it off of, so many samples. So we know that it can be off by a little bit. So that's why here it says, unbiased doesn't mean perfect, but means pretty darn close. And yes, it can be a judgment call, but again, there should be some reasonableness with your judgment. Now, the other thing that we'll talk about when we look at these sampling distributions is the spread. Okay? One of the things that will happen is, and one of the things that you can control when collecting samples, is how big of a sample you decide to choose. Okay? The biggest key and the biggest point to know is simply this. The larger your sample you choose, okay, the less variability there's actually going to be. Now this actually holds true, okay? But the one thing that you want to make sure, okay, is that, again, you want to make sure that your population is at least 10 times greater than your sample size. So once in a while, later on, we'll be checking this condition, not today. But the population itself, okay, doesn't influence the spread. But you want to make sure that when using the calculation, because of how probabilities can change, okay, when sampling without replacement, okay, you want to make sure that this condition still holds. But basically what it's saying is, hey, if you interview more people, your result is going to be a little more accurate. You're going to have less variability. Seems to make sense. Right? All right, so let's take a look at our last example. All right, so in this example here it says, the histogram below on the left shows the interval in minutes between eruptions of the Old Faithful geyser for all 222 recorded eruptions during a particular month. For this population, the median was 75 minutes. So here on the left, you have your population distribution, where the median of this distribution was equal to 75. There is one little typo here, and I'll correct it here in just a second. What a surprise, a typo in my notes. So it says, we use statistical software to take, and this should not say 505, it should say 500 simple random samples of size 10 from the population. Okay. The 500 values of the sample median are displayed in the histogram below on the right. So this is an approximate sampling distribution. We have 500 samples of size 10. Now it says the mean of the 500 sample median values is 73.5. Okay. So the median, or the average of these, was 73.5. So question A asks, is the sample median an unbiased estimator of the population median? Is this value unbiased? In order for it to be unbiased, what does it have to be? What does this value have to equal? Okay, it would have to be very darn close to 75. Is 73.5 really close to 75? Kind of, but when we're talking really close, we're looking for like 74.9 or 75.1. 73.5 is actually a considerable distance away. So is this an unbiased estimator? No. The sampling distribution median does not equal the population distribution median. Question B. Suppose we had taken samples of size 20 instead of size 10. Would the spread of the sampling distribution be larger, smaller, or about the same? So what happens is, here we took samples of size 10. So our sample median was going from 50 to 65. Notice how this is like the population, which is like sample size 1, 40 to 100. Notice how the variability got smaller. So if I go from 10 to 20, guess what's going to happen to this spread? If going from 1 to 10 decreases the spread, guess what going from 10 to 20 is going to do? Decrease the spread. Okay? So in our case here, we are increasing our sample size which will decrease our variability therefore making our spread smaller. All right, C. Describe the shape of the sampling distribution. So if we were to describe this shape, how would you describe it?
Bell shape, skewed
Okay.
to the left.
Okay, skewed to the tail's going to the left. So it is skewed to the left. So now it says, explain what this means in terms of overestimating or underestimating the population median. Well, to get this median here, we were taking the average or the mean of 10 samples. Okay? Since we're taking an average or the mean and it's skewed, okay, the mean is going to be pulled in the direction of the skewness. So the mean's going to be pulled towards the lower scores. Since it's getting pulled towards the lower scores, it would underestimate it. Okay? So since our mean is pulled towards the tail of the distribution, it would underestimate the population median. All right. That finishes up our note.